So what's up guys, welcome back to another video. So this is our first assignment of this module, Advanced Modeling. In this video we will be covering discriminant analysis. So let's get straight to the overview of the problem that is given here. It talks about a large manufacturing company that does special chemical processes for different types of aircraft parts. Some examples are Anoplate, Nadcap, NASF, etc. I hope I'm pronouncing these names correctly. Anyways, they usually do 2 or 3 different types of chemical processes such as anodizing, plating and non-destructive testing on the same part to make sure that the piece was correctly coated the first time. However, the company has been spending a considerable amount of money by doing the non-optimal process first and then adding the complement processes in stages 2 or 3. The industrial engineering team is looking for a solution so that they can predict which process will be most effective for new incoming parts with the least amount of second or third processes. This will save the company tens of millions of dollars by correctly identifying the most effective procedure the first time. Now below is the dataset of the last few years of the projects with the most effective processes and different material compositions. So this is the background of our problem. So let's jump into question 1, which says read in the data and make sure that column for optimal processing type is a factor. So we will read our data using the read.csv function and store it in the variable da_data. After this, we can check the structure of the data to understand it better. Now as you can see, there are 9 variables and all are numeric except optimal process type, which is integer. Now variables are self-explanatory. The first one is the process type and rest are metal compositions. Now as the question says, we will have to convert the optimal process type into a factor. So we know we can do this using the as.factor function as shown here. We have already done this earlier. So after converting it into factor, we can check the summary of the data. But I will be skipping this step. However, if you wish to know, you can check the summary as well. Now we'll move to next question. It says create a scatter plot of all the variables and explain. So we can use the plot function and give our data frame as the argument. Now for the scatter plot, we will exclude the factor variable, which is our column 1. After this, we can run this. And as you can see, our scatter plot is plotted. Now there is an explanation given here for the entire plot. So let's read the explanation. It says since this is a huge plot matrix, so explaining each plot will be a bit lengthy. And hence, below is the generic rules given to assess any scatter plot and same can be applied on it to understand it. So first point A is for direction. Positive gradient is when independent and dependent variable both increases. Negative gradient is when independent variable increases and dependent variable decreases. Part B is the form, which is to know if there is any association or not. It could be linear, curve, or just randomly scattered. Part C is the strength, which is basically assessed by checking how tightly the points are clustered in the identified form. It could be that there is no correlation, totally random points scattered all over. There could be a weak correlation, randomness is there, but some clustering of points can be seen around the identified form. Then we can have strong positive correlation, tight clustering in the positive direction around the identified form. Then we can also have strong negative correlation, which means tight clustering in the negative direction around the identified form. Part D is outliers. Any strange observations away from the cluster can be an outlier and demands further analysis. So these are few general pointers which can be used to interpret any scatter plot. Also there is a small note given here. It says scatter plot is to be used only for getting the glimpse of the data and it is to be used as an assistance in further analysis. So the above findings cannot be treated as conclusive. Now let's move on to the next question. It says run linear discriminant analysis and describe the output. So LDA function is a part of mass library. So we will load the library first. We will get these warning messages. Just ignore them. After this, we will use LDA function to build our model using optimal process type as the dependent variable and rest all the predictors as the independent variable. Second argument will be our data, which is stored in DA underscore data. Now here I have not created a train and test split as my focus is to demonstrate the process of LDA first. But if you want to create a train and test split, you are welcome to do it. After this, we'll run this and store it in the variable DA underscore data.LDA. Now as you can see here, the output is printed. And I also have included an explanation here. So let's read the explanation to understand the output. First, we have the LDA formula shown here. Second point says prior probability is there. Basically how the classes were distributed prior to running LDA. The proportion of training observations in each group. After that, we have group means, which shows the mean of each variable in each group. Then we have coefficient of LDA. Coefficient of linear discriminant basically provides the linear combination of variable to arrive at the decision boundary or to form the decision boundary. You may recall that linear discriminant projects the data onto new axes. So those new axes are nothing but linear discriminants. Now if you multiply each value of LDA, say LD1, the first linear discriminant, by the corresponding elements of the predictor variables and sum them, you get a score for each respondent. This score along the prior probability are used to compute the posterior probability of class membership. There are a number of different formulas for this. So classification is made based on the posterior probability, with observations predicted to be in the class for which they have the highest probability. These coefficients of linear discriminant are of the separation plane. These coefficients also give information about the influence of the variable in the group. That is, higher the coefficient, higher is the influence of the variable in the group. Now if you see the coefficient of linear discriminants, there are two coefficients. Now the question is, why there are two coefficients? So for this, you need to understand how discriminant analysis works. However, it will always be total number of class minus 1. So now let's understand how does it work. Recall that LDA projects the data onto a new axis. So if it is a 2D data, then it is projected on 1D. And if it is a 3D data, then it is projected on 2D, and so on. Now here we have three classes. So we have two coefficients of linear discriminants. To elaborate more, let's get back to the concept. So what DA does, say if you have three categories of voters, Democrats, Republic, and Independent. LDA will basically reduce the problem into two variable problem by making first combination as voters are Democrats and non-Democrats. This will give us first LD coefficient, and then second combination would be non-Democrats as Republicans or Independent. This will give us the second LD coefficient, and hence the number of LD coefficient will always be minimum number of classes minus 1, or it could be equal to number of predictors. Now you may ask how linear discriminant selects these combination. LD selects these combination to optimize the results. That is, first group provides maximum discrimination between two groups, second provides the second most discrimination between groups, and so on. This is called canonical analysis. Now we don't have to go into the details of it, but just understand LD selects the combination by optimizing the results based on the maximum discrimination between the groups. But an important point to note here is that these coefficients do not tell us between which of the groups category the respective function discriminate. We can identify the nature of discrimination for each discriminant function, that is canonical function, by looking at the means for the function across groups or categories. You can see the means in the output. We can also visualize how the two functions discriminate between groups by plotting the individual scores, say LD1 versus LD2 for the two discriminant functions. Now last part in the output is the trace. The trace tells us that how much of the variability is accounted by each discriminant. Basically, it is the percentage separation achieved by each discriminant function. In our case, LD1 and LD2 shows 64.2 and 35.7% variance that is accounted by the two discriminants respectively. So this was a pretty long explanation, but I hope you have got the clarity now that how discriminant analysis works. Now we will move to the next question. It says predict and then plot the histogram of the predicted data. So a nice way of displaying the results of a linear discriminant analysis is to make a stacked histogram of the values of the discriminant function for the samples from different groups. So we will use predict function to make the prediction. So the first argument will be our model. And for data, we will use our original data as we don't have any test data. So we can run this and store it in the variable LDA_hist. Now there is an explanation given here for the predict function. So let's read the explanation. Also, I have not displayed the output of the predict function because it's a long output and there is no point in printing it. You can check the output on your own if you want to. However, there are three things that predict function return, which are given in the explanation. So let's read the explanation now. First is class. So the predicted class of the new observation is based on our model. Next is the posterior probability, which is the probability of a particular observation row belonging to a particular class. And third is x, which is basically LD1 and LD2, which are the coefficients of discriminant of the separation plane. We already know that for n class, it will be n-1. Now let's plot the histogram and see our output. We will use the function LDA_hist. So as you can see, the first argument is the coefficient of linear discriminant, and the second argument is the dependent variable, which is optimal process type. So we can run this, and this will give us the histogram for the first linear discriminant coefficient, which is LD1. Now again, explanation is included here. So let's read the explanation. It says that there are three histograms which are showing here. The three histograms is showing the separation according to the groups. It can be concluded that group 1 and 2 are well separated. However, there is an overlap in group 2 and group 3. And classification of class may lead to high misclassification error. Similarly, we can create another histogram for the second discriminant coefficient as shown here. And again, an explanation is given here. It says it can be concluded that group 1, 2 and 3 all have some overlap, as you can see from the histogram. And the classification of class may lead to high misclassification error in this region. So that is how you interpret the histogram. Now we will move to the next question, which covers the prediction accuracy of our results. So for this, we can create a confusion matrix and check the accuracy of our model. We will use the table function to create confusion matrix as shown here. So the prediction results are in LDA_hist variable. So we will subset this variable using the class object. And then the second argument is our dependent variable, which can be subsetted from the original data. So we can run this and store it in the variable cf_table. And after this, we can sum the diagonal elements and divide it by total to get the accuracy rate. Now this turns out to be 98%, which is like way too good. But we should not get excited about it. This is because we have used the same data to train the model and test it. So there is nothing great about our results. But anyways, this was just to give you a demonstration. You can very well create a train and test split and perform the LDA in the same way. Now with this, we will conclude the assignment. So let's quickly revise what we have learned so far. First, we created the LDA model. Then we have seen in detail how to interpret the output of LDA model. After that, we made the prediction and learned about different objects in the output. After that, we plotted the histograms to see the separation of different groups. And finally, we created a confusion matrix to check the accuracy of our model. So I hope by now you have got a fairly good idea about model building. Now we will take one more step in learning the advanced modeling and study clustering in the next video. So until next time, have a great day. See you.